Okay, for this video, we'll be talking about electrical system, right? So please have your notes ready. You can download it from Google Classroom. So the first page talks about the learning outcome. We actually translated it to success criteria, meaning what do you need to actually do for this chapter, right? So the first success criteria is that you can draw and interpret circuit diagrams and set up circuits containing electrical sources, switches, lamps, resistors, either fixed and variable, and ammeter and voltmeter. Okay, next is I can describe current, potential difference, and resistance of an electrical system and stating their SI units. And after that, you need to be able to apply the relationship V equals IR to solve problems. So this is actually a formula. So there's actually calculation involved in this chapter. Okay, so you have actually done this in PSLE, the components of an electrical system. So a simple electrical system must consist of an energy source, right? So it can be a cell. Okay, if I have two or more cells, then it is called a battery. Okay, so we have a cell. It must have a switch for turning on and off the electrical system. A bulb, so this bulb is actually what we use the electrical energy for. Okay, so there are of course wires. So in the lab, let's say we are doing some kind of experiment. The color of the wire doesn't matter. We have two colors, red and black. The color doesn't matter. Now in the exam or WAs, we will be asking you to draw the electrical system. So of course, asking you all to draw this system using pictures is not very efficient. Okay, so we can actually simplify the above by drawing symbols, okay, to represent the different components. So you need to be able to use the symbols to represent it. Okay, so components. So the cell is represented using this symbol over here. Okay, so take note here, this is plus, you can see from here, and this is minus. If you look at a battery, you will see the plus and minus. So later on I'll elaborate again, but the long side is the plus part, plus plus pole, and the shorter is the negative. Okay, then the switch is like that. So if I want to draw a open switch, then I'll draw this symbol. So this is a closed switch. Okay, so by right, the bulb, which is a component using the electrical energy, will actually light up. So basically it's a circle with an X. Then draw your wires with straight lines. Okay, so you'll be required to draw and interpret circuit diagram. So maybe I can have a real life photograph, and you must use the symbol correctly to represent the electric circuit. Okay, so there are some more symbols to recognize and draw in circuit diagram. So like what I said just now, the electric cell consists of one set of long vertical line and a short vertical line. Okay, the long part will be positive, the short part will be negative, right? So if I connect them in series, two or more, then it is called a battery. Okay, and of course I must connect them in the correct polarity, plus to minus. Next, we have ammeter. What does ammeter measure? It actually measures current in a circuit. Okay, it measures current in a circuit, and it also has polarity. It also has plus and minus. I will elaborate later. The next symbol that you need to know is the voltmeter. It measures potential difference across an electrical component. It also has positive and negative, which I will elaborate later. Then we have fixed resistor. Okay, so fixed resistor, it actually converts electrical energy to heat energy, right? Then we have variable resistor. The symbol is almost the same, except that instead of just the triangle, we have an arrow. Okay, it doesn't matter what is the direction. Okay, so I can have this as well as a variable resistor. Now, what is the function of this? It actually controls the current in the circuit, okay, by changing its resistance. So the amount of current flowing in the circuit can be controlled by using a variable resistor. Where do you see this? Sometimes your phone, the volume button is actually a variable resistor. The fan speed, right, we turn from speed 1 to 3, there's also variable resistors involved. Okay, so if I want a faster fan speed, I can actually reduce the resistance so that more current flow. Okay, so generally more resistance, okay, more resistance, it will result in less current, okay, and vice versa. Okay, then this is the electric lamp. Electric lamp, there is no polarity, similar for fixed resistor. There's no plus and minus. Okay, so it converts electrical energy into light energy. Then we have the switch open and the switch close. Remember to draw in the two circles, even if it's a closed switch. If not, I wouldn't know whether it is a switch if you just draw it this way. Okay, so it opens and closes the circuit. Right, so you need to know the symbols, know the name, as well as the function. So you need to memorize this table. Okay, let's move on. We talk more about the components of an electrical system. Okay, the cell, which is a source of energy, it actually stores chemical potential energy, which is then converted to electrical energy so that it can drive electricity within a closed circuit. Okay, one side is positive. Do you remember which one is positive? The long is positive, the short is negative. Okay, then what are electric charges? It consists of negatively charged electrons, right? You have learned in your chemistry lessons, electrons are free to move, right? So only electrons can move. So make a guess, which part of the battery will the electrons come out from? Bearing in mind electrons are negative, okay, I'm going to have electrons coming out from the negative terminal. Okay, now electrons flow in a direction towards the positive terminal. Why? Because if this terminal is positive, electrons being negative will be attracted towards this positive terminal. Now, of course, we need wires to connect the different components so that the charges can flow. This is to allow electric charges to flow. Then, what is the purpose of using all this electrical energy? Right? We actually have bulb and resistors. They are able to convert electrical energy to other forms of energy. Bulb, it can either give off light and it will also give out some heat energy. Okay, so these are the main components. Okay, then I think you learn about this in primary school, open circuit and closed circuit. So when the switch is open, the bulb does not light up, right? Because this part is positive, this part is negative. Electrons come out from the negative component, but now let me tell you that the current, okay, actually comes out from the positive. This is important. Current comes out from positive, electron comes out from negative, right? But mainly in our syllabus, we'll be focusing on the electric current. So if I were to ask in WAs an exam, right, label the current that flows out from the cell, you have to draw in this direction on the wire because it is the charges that is moving, the current that's flowing in the wire. You have to draw this correctly. Okay, that means the direction is important. Now, current is a long word, so is there any symbol that we can use to represent current? It is the capital letter I. Right, so now that we know current is represented by I, we can then add in I. Okay, so now example, I have two cells arranged in series side by side. This terminal is positive, this terminal is negative. If I were to ask you to label the direction of current, okay, maybe let me just add in light bulb, and this is a closed circuit. Okay, If it's a closed circuit, I want you to label the current. So you can do this with the arrowhead. You can represent it using letter I, and this current will continue into the light bulb. Okay, and eventually it will flow back into the cell. Okay. However, for this case, because of the open switch, the charges are not able to flow. Current is not able to flow. Therefore, of course, the light bulb will not light up. Okay. But now, when the switches are closed, when the switch is closed, this will be known as a closed circuit. So, please do with me. This is positive. This is negative. If I want you to label the direction of current, it must come out from the positive. Okay, this is the current and this is the current. The current will deliver the energy to the light bulb, therefore the light bulb will glow, and this current will actually go back to the cell. The current will not be used up. Okay, after this, after it has given energy to the light bulb, the current will still continue moving back. Okay, so it can get more energy from the cell and continue this process. Okay. So essential takeaway is that the components of an electrical system work together to allow the flow of charge in a closed circuit. Okay, so now we go into some more terms. This is a definition for electric current, right? Electric current, like what I mentioned just now, it is denoted by a letter, capital letter I. It is the rate of flow of charge. Okay, so rate is how much, okay, per second, right? If I ask you what is your typing rate, yeah, or what is your rate at McDonald's, it is maybe $5 an hour. Okay, what's your typing rate? Maybe 80 words per minute, things like that. But for here, current I is the rate of flow of charge, electric charges, right? So the rate of flow of charge refers to the amount of electric charge flowing past a particular point in an electric circuit per unit time. Okay, but if you want to memorize, you just memorize that electric current I is the rate of flow of charge. Now, of course, logically, the greater the rate of flow of charge, the larger the current. Now, this is also important. SI unit of electric current is the ampere. Okay, please use capital letter A to denote the unit. But if I were to ask you to spell out what is the unit, okay, you have to spell it in small letter A, ampere, A-M-P-R-E, named after a French scientist. Okay, so this is the current. So just now we actually talked about electron flow and current, right? So I was saying that, example, now if you look at this battery, right, this part is the positive, so I should use a long line, long vertical line to show that it's positive, and this side is negative, the short one will be negative. Okay, so I'm representing this circuit using the symbol, which is much easier to draw. Okay, so because before the scientists discovered electrons, they wrongly believed that electric current is caused by the movement of positive charges. Now, if you link back to your chemistry, positive charges, I can take it that they are protons. However, protons are not able to move, right? They are fixed in place. But the electrons are actually the one moving. Okay, so so before that, they thought the electric current was caused by the positive charges. Okay, although this idea was later proven wrong, the idea remains, right? So the movement of positive charges is called conventional current. So I will now, instead of saying that is the movement of positive charges, I call it the conventional current I. Okay, I call it the conventional current I. Alright, but actually the electric current is caused by the flow of electrons. So electrons will be coming out from the negative, right, So we will have two directions, okay? But the main focus will be on conventional current. So when will I ask you for the flow of electrons? So if I'm setting a paper and I need one more mark, I can just maybe include it in my electric circuit and say, label the direction of flow of electrons. Then you will have to give me this answer. Okay, if not, if you are talking about current in our syllabus, it is this guy that we will focus on. Okay, this is the flow of conventional current. It always comes out from the positive. Okay, so please take note. You can refer to this diagram. How do we measure current? We use a ammeter to measure the current. Okay, you can see from here, the red color is positive, the black is negative. So if I were to represent it, I will have a plus, I will have a minus as a circuit symbol, right? It will be impossible for you to draw this in the exam. So we will just use a capital letter A with a circle to represent your ammeter. So we use ammeter to measure current flow. Okay. Now, how do we connect an ammeter? This is important. An ammeter is always connected in series. Why is that so? Because the ammeter is measuring current. It is measuring current, right? And this current is actually flowing in the wire. It flows in the wire. So definitely my ammeter that measures current must be placed in the path of the current so that I can measure how much current actually flow through it. Okay, so it's like your wind vane, right? Your wind vane is measuring the speed of wind, right? So it must be in the way of the wind so as to measure how strong the wind is. Or a water wheel. Okay, for a water wheel, we actually put it in the path of the river so as to measure, to see how fast the water wheel turns, then we'll know how fast the river is flowing. Okay, so you need to take note of the plus and minus. Now, if you look at this circuit diagram made of real life components, do you see anything missing? Do we have light bulb? Yes, we have light bulb. Does light bulb need plus and minus? It doesn't, right? The light bulb will light up as long as current flows through it. Okay, then we have our plus and minus. We have our cell or battery. In this case, it should be battery, right? Because we have three cells connected in series. Okay, three cells connected, it becomes a battery. Remember, battery is containing two or more cells. Then we also have ammeter, so we are actually lacking a switch. So in this case, it is not really connected according to what it is. Okay, so maybe I should do light bulb very quickly. Okay, I have a switch that is closed. Then I have plus and minus, plus and minus, plus and minus, right? Plus and minus. So I have plus here, I have minus here. Then over here, I have my ammeter. So now ammeter, take note, it must be positive connect to positive, negative to connect to negative. What do I mean? So over here is the negative terminal of the battery. So on the left hand side, it must also be negative. Remember, negative must be connected to negative. Over here, if it's positive, if you run through this wire, it is actually connected to the positive. So, yep. So remember, positive to positive, negative to negative for ammeter. What do the ammeter measure? It measures current flowing in the circuit. And how is it connected? It's always connected in series, right? Because I want to find out how much current actually flows through the light bulb. So it must be in the way of the light bulb so that I'll know how much current is flowing. Okay, before I go to electric cell, I would like to do a very quick recap of what we have learned about current. Okay, current is represented by letter I. Okay, current comes out from positive terminal of the battery. Okay, how do we measure current? Current can be measured using ammeter. Okay, ammeter, it is connected in series. Okay, and ammeter, there's plus and minus, so it is connected plus to plus, minus to minus, and connected in series. Very important. Then sometimes I may ask you for direction of electron. So this is my current. So coming out from the negative terminal is my electron, which is negative. Alright, but most of the time we'll be focusing on current. Okay, so this is the quick recap. Okay, then we move on to the next component, which is the electric cell. In an electrical system, the cell supplies energy for electric charge to flow in a closed circuit. That means this electric cell is driving the charges to move around the whole circuit. Okay, so this, you can think of it like a water pump that is providing energy to drive water around a closed water pipe. Okay, this term is new. We have done current, so now we do potential difference. In this chapter, we actually have a formula called V equals to IR. Okay, so which one have we done already? We have done I, which is actually our current. So now we are actually doing potential difference V. Okay, so this is the definition. The potential difference V between 2 points in an electric circuit is the amount of energy needed to move a unit charge from one point in the circuit to another point. Okay, so it's a very lengthy definition that you need to memorize. Sometimes we refer to potential difference as voltage. Okay, so there's a lot of V. SI unit of potential difference or voltage is the volt. Okay, so it is used by we use V, capital letter V, to represent volt. Okay, so voltage is the potential difference. What is it? It's actually the energy needed, okay, to drive or move a unit charge from one point in a circuit to another. Okay, the unit for voltage is volt. Okay, capital letter V. Okay, so since we have done V and I, so I will just quickly summarize potential difference. Okay, it's also known as voltage. Okay, so this is the name. Okay, then the symbol to represent potential difference is V. Then the unit is called volt. And the symbol to represent volt is V. Next we have current. Okay, so the symbol is I. The unit is ampere. And we use capital A to represent it. Okay, so you need to know this. Students always confuse between I and A. They will say current is A. Okay, yeah. So you need to know this. Now, measuring potential difference of voltage, we use a voltmeter to measure the potential difference between 2 points. And if you see from the diagram, there's a positive and there's a negative. Okay, so again, we have plus and minus. We have different polarities, or a positive terminal for voltage and negative for the voltmeter. Yeah, sorry. Okay, so how do we connect a voltmeter? Voltmeter is connected parallel. Do you still recall? For ammeter, it is connected in series. Okay, ammeter is connected in series. Okay, so parallel means there must be another path, right? So it is not in the same path as the current, because what is used to measure current? If I want to measure the current flowing in here, I will have to put a ammeter here. Okay, and this side will be positive, this side will be negative. Remember, negative to negative, positive to positive, and ammeter is connected in series. But for the voltmeter, it must be connected parallel. That means it is in another path. Okay, the current actually flows this way. Very little current flows through the voltmeter, right? So what does the voltmeter actually do? To put it simply, it measures the difference in energy before the component and after the component, right? So if you think about it, the current actually carries, the current that leaves the positive terminal actually carries energy, okay? It carries energy, right? So if it travels along the wire, okay, it's like a very smooth path for them, very low resistance. The wire has low resistance. So imagine you're walking along a road of low resistance. You wouldn't lose much energy, right? You wouldn't lose much energy. So the energy that the current have up to this point is almost the same as before it leaves the battery, okay? And after it passes through the light bulb, which has high resistance. Okay, the light bulb has high resistance because that is the whole purpose. It has high resistance, the current find it will transfer the energy to it, and so the light bulb will glow. And after it passes through it, if we were to check on the current here, it will have lower energy, right? It will have lower energy. So the voltmeter actually measures before, the energy before it passes through a component, to the energy after it passes the component. Okay, so it's a little bit like let's say like for Mr. Lee, he leaves his house, okay, and on his way to school for a class, right, he will still be quite happy, still have a lot of energy. But after he went through a class, he will be depleted of energy. He will be depleted of energy, right? Let's say the class is very noisy, never bring PLD, never do homework. He'll be shouting at the students. He will be depleted of energy. So where do we have the highest energy? It will be this section here. Okay. Then after that, once he leaves the class, his energy is almost zero. He needs to go back home and rest. So if I were to connect a voltmeter here, before and after, right? The voltmeter will be able to observe the energy before and energy after. Okay, so this is what the voltmeter does. It is to measure the potential difference or the energy across it. Okay, so voltmeter is used to measure potential difference. What is potential difference actually? It is called, or if I put it in English, it is actually the difference in potential. Okay, so over here is high potential, and after passing through the component going back to the battery or the house is low potential. So since there's a difference, it is being measured by the voltmeter. Okay, I hope I didn't really confuse you all. So now we go to the third term, which is resistance R. So in layman's term, resistance R of an electrical circuit component is a measure of how much the component opposes the flow of electric current. Okay, so now since we know the symbol for R, R is high. That means I will be low. Okay. Electrical conductors have low resistance to current. So example will be your copper wire. They have very low resistance. Insulators, however, have very high resistance. Now, SI unit of electrical current is the ohm. Okay. So since just now we made a summary of the terms, we will add in one more. Okay, so we have just learned resistance. Okay, the symbol for resistance is R. The unit is called ohm, and the symbol of this omega is used to represent ohm, because ohm is OHM, right? It's quite troublesome to write all three of this, so we use omega symbol to represent the unit ohm. So example, if I were to write in a question, resistance of a lamp is 4 ohm. Okay, so I can actually translate it to R, because resistance is R, equals to 4 ohm. Okay, so I'll read this as R equals to 4 ohm. Okay, but I don't write it out as OHM. I put it as the symbol omega as a short form. Okay, how about this? Current in circuit is 10 ampere. Okay, that means I is equals to 10 ampere. Okay, so this is how we use a symbol. Please memorize the name, the symbol, the unit as well, and the symbol used to represent the unit. Okay, so you actually learned this in primary school, right? So materials such as electrical conductors allow current to flow. Okay, then insulators do not allow current to flow. I think this one you all can read through. Tungsten and nichrome, they are quite special materials. They are conductors, but they have very, very high resistance. Okay, it's high, so that most of the energy is converted to other forms of energy. Okay, so tungsten and nichrome, they're used in a light bulb and also heaters. Okay, the purpose is we want the electrical energy to be converted to other forms of energy like light and heat energy. So when I have tungsten and nichrome that is high in resistance, the electrical energy that the current is helping to transport will actually be converted to heat and light energy. Okay, but we also have electrical conductors that have very, very low resistance, like copper and silver. They are used in our wires, okay, in our cables. Okay, then electrical insulators will be like plastic and glass. They do not allow current to flow. Okay, sometimes we use them in safety boots. Okay, then resistors, they are components that reduce the flow of current in a circuit. Okay, there are two types of resistors: the fixed resistor, where the resistance is fixed, and the variable resistor. We use this term called rheostat. Please make sure you know how to spell it. It can, the rheostat's resistance can actually be varied. So this is the a diagram of how the rheostat will look like. When we are doing our experiment, you should be able to see this in the lab. We also have a lot of fixed resistors. Okay, so what is the effect of adding resistor? When a resistor is added to the circuit, the resistance increases, right? As we have more and more resistor, definitely the resistance increases. So just now I talk about it. When R increase, what happens to the I? The I will decrease, and vice versa. So with more resistance, it is more difficult for the electric charge to flow, so we have less current. Okay, so we look at this example. We have a cell, we have a switch, which is a closed switch, and we have a bulb. So there is no other resistor. Therefore, most of the energy from the cell will be given to the light bulb. So the light bulb will glow very brightly. But then we added a resistor here. Okay, so now the energy will have to be given to both the resistor and the light bulb. Okay, so of course the cell contains limited energy. So now I have to pass some energy to the resistor. Therefore, the amount of current, the amount of energy that the current carries will definitely be lesser, so the light bulb will be less bright. Okay, But later on when we do our calculation, you'll find that the current that is in charge of carrying the energy will be lesser. Therefore, lesser current, lesser energy carried by the current. Therefore, the light bulb will not glow as bright. So this is the relationship V equals to IR. Okay, the resistance is the ratio of the potential difference V across the component to the current flowing through the component. So there is V across. Just now we talked about voltage or voltmeter must be in parallel, right? So this is the resistance. Then my voltmeter is in parallel. Then I have ammeter, which is in series. So this ammeter can actually measure the current, right? So it has to be within in the path of the current so that it can measure it. But voltmeter, it has to be connected in parallel so that to measure the difference in potential or the potential difference. That's why V is across, potential difference V is across, current is flowing through. Okay, so we have this formula V equals to IR, right? I like this kind of one-liner. I think some of you still like to use this triangle. Okay, so is it this way? So if I, yeah, yes, okay. But I prefer this because I can really see the relationship. If R increase and V is fixed, then your I will decrease. Okay, so try to memorize this as the formula, although this will work as well. Okay, so now we do some example. A resistor with resistance R, so I have R as resistance, has a potential difference of 1.5 volt across it. So maybe if I put it into a diagram, I have a resistor with resistance R. It has a potential difference of 1.5 volt across it. So how do I represent this 1.5 volts? So I need you all to do this, write 1.5 volts, and it must be from the start to the end. Okay, that means before the resistance and after the resistance, we have a potential difference of 1.5 volts. And the current through the resistor is 0.38. So over here will be I equals to 0.38. Please copy this. Okay, so voltage must be across the component. So this is how we represent the voltage. Current must be flowing in the wires, okay, through the circuit. So the current here is also 0.38. Okay, so how do we calculate the value of R? By using V equals to IR. So the question is, the question gives us our I given, our V is also given. So by rearranging, R equals to V over I, right? Because now I is multiplied to R, and I want R to be alone, so I need to bring I over to the other side. That means in my math, I will become the denominator. So now my V is 1.5, my I is 0.38, and the answer will be, in my calculator, it is 3.9473. Okay, but we leave it in 3SF for our calculator answer, so it's 3.95. Now what is the unit of R? It is in ohms. Okay, so this is the first example. So V equals IR. Yeah, okay, so for this video we'll stop here. Okay, I will do another video.